Welcome to this webinar on the Thalweg Tracker. I will start by introducing the Thalweg Tracker, what it exactly does and where it fits in our other trackers in OpendTect. Then I will give a number of examples for seismic Facies tracking and how you can use the tracker for machine learning applications. And I'll round it off with a small demo. Now, in OpendTect we have quite a few trackers. Obviously we have conventional auto trackers, and these work on tracking the amplitude, the phase and correlations, optionally snap to an event. And this is for tracking horizons. So let me show you an example. Here it is. This is an OpendTect feature. It's free, it's open source, and of course this is well known as our horizon tracker. Now then we also have more advanced trackers, inversion-based flattening algorithms. Two of them, Inversion and Inversion Plus, also for horizon tracking, but these are tracking the dip field, and Inversion Plus also uses the amplitude. These are used for tracking unconformities. That is the inversion algorithm, and the Inversion Plus is for tracking seismic events, horizons that are snapped to an event. The idea is that we try to flatten the dip field. We do that by introducing a grid through a number of manually picked positions. We calculate the dip of the grid, and we also compare that with the dips that have been measured from the seismic data, and we try to minimize the error. This is an inversion process. Eventually we have alignment between the dips of the seismic and the dip of the grid, and that is our horizon. If we only use the dip, then we can use this for unconformity tracking, and if we want to snap it to a horizon, then the process is the same, but in between the inversion loops we then introduce more grid positions, seed positions on the grid that will be honored exactly, and this is done by using a very constrained amplitude tracker. Now here we see an example of the inversion, the unconformity tracker. We start with a flat horizon, in this case the red horizon, then we iterate one time, 5 times, eventually after 20 times we have found the optimum and we have a mapped horizon. This we can constrain with as many points as we want, so we can really force the algorithm to go to the points that we have clicked ourselves. And that is so for the unconformity tracker, the inversion algorithm, but also for Inversion Plus, where we also snap it to the horizon, and in between the inversion loops we add more of these seed positions by conventional auto tracking. And then we also have automatic fault extraction, and that is based on tracking the fault likelihood with its dip and strike components, and that is part of the faults and fractures plugin. And here we can constrain this by tracking only the largest faults, or only faults in a certain direction, a certain dip, and so on. And then we come to the Voxel-based connectivity filters. We have a conventional Voxel-based connectivity filter that operates on absolute amplitudes, and that is used for tracking 3D bodies. And here we see an example, and we can use that to track bodies and also to rank these bodies according to size or other features. This is also an OpendTect feature, so it's free and open source. Now then finally we come to the Thalweg Tracker, which is also a Voxel-based connectivity filter, but it operates on relative amplitudes, and this is used for tracking seismic Facies, and I will now explain in more detail what actually this Thalweg Tracker does. So it's an OpendTect Pro feature, so it's part of the commercial version. It's a special kind of 3D connectivity filter, so a voxel connectivity filter, and the trick is that we follow now the path of least resistance, and that is the Thalweg, used for seismic Facies tracking and also as input generator for machine learning workflows. The initial version was developed by Mike Pellissier. The Thalweg is a German word. Tal means valley, weg is path, and the Thalweg is the line of the lowest elevation inside a valley, and that is the course of the water in, for instance, a river. In seismic applications, in our Thalweg tracker, we've defined this as the seismic amplitude tracker that follows in 3 dimensions the path of least resistance. And let's see how the Thalweg tracker does that. We start from a single voxel, a single seed position, and then the algorithm evaluates all the cells neighboring this seed position. Here we are evaluating only the 6 cells at the sides, but you can also have more cells to evaluate on the connections and the corners and so on. The idea is that after we have evaluated all these neighbors, we are adding only one of the cells in this growing body. Not all of them, as we do in a conventional voxel connectivity tracker, but only one. And the one that we select is the best cell to add, and the best one is defined as either the value with the most maximum amplitude or the one with the largest minimum amplitude, and that depends on whether we started from tracking a minimum amplitude or a maximum amplitude. Now, once we have added one cell, we repeat the process. Again, we are evaluating all the neighbors. We rank them according to minimum to maximum amplitude, and we add the one that fits best. Now, we have a variation on this theme, and that is called the margin tracker. And that is that we say we're not going to just add one, but we are adding a certain percentage of the elements that fit. And that can be a constraint like 5% of the best elements will be added at any iteration. If you would add all of them, so the 100%, then the margin tracker becomes a conventional voxel connectivity filter. Now, one of the nice things about this tracker is that we have seen time and again that if we start tracking from one single position, the tracker really follows a path that has apparently been laid down or been implemented by the sedimentation process. So in this large picture we see we started from one seed position, and the colors indicate the history on how we actually grew the body from this single seed position, from 1 to 50,000 voxels, 50,000 cells. In the smaller picture, we have virtually the same object, the same set of points have been tracked, but now from a completely different position on that same channel. And we can see that the shape and the cells are the same, but only the colors are different, and that is because the history of this growing object was different. Now, this history is playing an important part in our interpretation, because we start from a single seed position, and at some point we see that the tracker is leaving the seismic Facies that it is tracking, and it spills over into the next Facies. On the left we see a channel tracked from one single seed position, 50,000 cells, and it's all part of a channel complex. Nice channel Facies, but if we go to 80,000 feet, we see that some features are added which we probably would interpret not as being part of the channel Facies, but of some other Facies, as in this case the splay Facies that is spilling out from this meandering system. So we know from the history exactly where this happens, and this means that we can isolate the channel quite easily by reducing the number of voxels, the number of cells to track. At the same time, if we drop a seed inside display facies, we could track display facies. So that is indeed what we are doing. We're typically tracking a large number of cells, and then we look at where the object is spilling over in other objects, other seismic facies. Then we dial back, and we may or may not use the margin tracker to grow the body in size, make it a little bit fatter. Now let's look at a few seismic facies examples. I've selected 4 different examples, one from Canada, Penobscot dataset, free dataset in OpendTect, available from our Taranaki website, a dataset from Ireland, Porcupine Basin, a free, well-known, also free dataset in OpendTect, and then one from China, the Zhao oil field in the Bohai Basin. Bohai Bay, let's start with that one. This is a highly compartmentalized reservoir. We have numerous fluvial channel stack deposits, and we are going to use the Thalweg Tracker to isolate these channels, used for well planning and to direct our horizontal producers and high angle injectors based on seismic amplitudes and the objects that we extract from the data. On the left we see our stacked channels on the seismic, and in the middle we see some of these channels which have been tracked and then also been made a little bit fatter using the margin tracker. And on the right we see the channel which is indeed stopping against fault departments as visualized with this thin fault likelihood overlaying on the seismic. Now here we're looking at a comparison between absolute and relative amplitude organization. The same channel, we're visualizing the amplitude on top of these extracted cells, and the amplitude is typically used as a lithology fluid indicator. Whereas we're looking at how the body actually grew, we can say something about the sedimentation process and how the sediment actually was deposited. This is still debatable on what interpretive value these relative organization has, but we're pretty sure that it has relevance, and it's really what the Thalweg Tracker actually is exploiting and why this works. Porcupine Basin in Ireland, we see incised values at the base Cretaceous and conformity. The channel here on the left, lower left upper corner, has been extracted, and we're slicing through the upper part from A to B, and we see the channels on the seismic, and this is the cutout through the body that has been extracted using this Thalweg tracking algorithm. In the Netherlands, F3, we see these faucets. We're dropping a seed in them, and it appears that this is following all kind of sand waves. And here we see on the left 1500 points tracked, and on the right, sorry, even more. I don't know exactly how many points, but this is the amplitude displayed on a number of sand waves, and on the right we see more sand waves tracked because we have tracked more voxels with the Thalweg Tracker. And here we see actually the tracking order. On the left it was 100,000 voxels, and on the right 200,000 voxels. But we're still following the same sedimentary facies, all sand waves. Penobscot, this is an interesting sedimentation because it is a mixed siliciclastic carbonate facies. We have reef deposits, we have a carbonate facies system with carbonate slope basinal facies, and we also have sediments coming in via a channel which is ending in this channel lobe. On the left we see a spectral decomposition at the top Taranaki formation, the reservoir in this case, and if we're looking at the random line from A through these reefs and through the channel lobe, then this is what we see. We see the reefs and we see here the channel overlaying it. On the left, the extracted bodies using the Thalweg Tracker, both for the reef and the channelized lobe. And if we now compare this with a conventional auto tracker, you can see the auto tracker in a conventional way, so that it just would not create a shape like a channel. It would just extend in all directions equally, and we've lost this this organization of the deposition, which is apparent in the Thalweg Tracker body that has been visualized and tracked on the right. Now, how can we use this in machine learning? I give you two examples. For machine learning, if we are using a workflow which is depending on picked labeled positions, then this labeling can be done in different ways, and it depends on what kind of workflow you're following and what kind of object you're trying to track. Whether you're going for either manual picking or even drawing of the objects, then you need macro scale type of objects like seismic chimneys, salt domes or fault. These can be tracked manually because they're large enough. But you can also use paintbrushes to drop a lot of seeds inside such a body. If you go at a smaller scale, then you can't do that because a paintbrush would be much too inaccurate to drop the seeds where you really want them to be used. And you also need so many points for a convolutional type of neural network that you can't pick them manually. So you need to have a different way of generating these labels. And the Thalweg Tracker is one of the ways to do this. Now, the first example is this stacked reservoir channel and fluviatile sedimentation process where we see all kinds of geomorphological features. Some of them are very clear. Everybody will recognize that this is a channel. Others are more difficult to interpret. But based on the shape of these objects that are being tracked and also their spatial position relative to each other, we can use these as labels for representing a specific seismic facies. As the tracker is only either tracking positive amplitudes or negative amplitudes, we have created here 4 times 2 facies, so for positive and negative amplitudes. In total 8 different classes representing meandering channels, unconfined channels, splays and floodplains. And then we downsampled these using the tools in our point set library, such that we had equal numbers of examples for all these different classes. And at each of these points we then extracted a pizza-like box of seismic. We see here one of these pizza-like slices in terms of inlines and cross lines and time slices, and this is for one of the channel classes. And These boxes with all these labels were then given to a convolutional type of neural network, a net type of model that was trained to recognize the seismic and separate the seismic into these 8 different classes. What we're seeing here is the application of the trained model. It created the seismic Facies output, and we have used a Wheeler transformation, a flattening of the seismic using a horizon cube to really follow these channels as best as we can, and we're slicing through the seismic Facies cube at 2 different levels. Now this is a lengthy process because the processing time that it takes for what we call an image to point prediction is very large. The training is not a big problem because the models are relatively small. The labels are no problem. We've generated them with the Thalweg Tracker. But the application, the CPU time it takes to generate this volume is quite large. So once we have created a small piece of the data, we can then use an image-to-image model going from seismic in blocks to a seismic Facies cube. The training of such an image-to-image 3D unit is large. It takes maybe several hours to maybe a day. But once we have trained that model, we can apply it really very fast to generate huge output volumes of this seismic Facies cube, and that is what we see here on the right. So this is just to save time, but it is a workflow where you can speed up the process by using 2 different types of predictions. Now the last example I'm going to show is an example again by Mike Pellissier. He used the Thalweg Tracker in combination with attribute volumes and to actually extract 3D bodies of these incised turbidite channels. This is from the Taranaki Basin in New Zealand. And we see these V-shaped turbidite channels. And this workflow is quite interesting. What he uses is a 2-pass gradient. This is the second derivative along cross lines. So a new attribute volume is created. And then he uses the Thalweg Tracker to create labels for positive Thalwegs and negative Thalwegs. Then the next step is to use the paintbrush to create a third example set. And he is painting the outside of these bodies to represent the background. Then he extracts couplets around each of these 3 examples, 17 by 17 by 33 samples, puts them into a net convolutional neural network to classify the data into 3 channels, positive Thalweg, negative Thalweg, and outside the turbidite channel. And then he applies this convolutional neural network. You get output likelihoods 0 to 1, and then he does a post-processing on these volumes to create the desired output. So this is step number 1, creating an attribute, the 2-pass gradient. Then he tracks with the Thalweg Tracker the positive edges of this system. And he does this for positive and negatives. And then this is the result of the positive and negative Thalwegs likelihood inside the turbidite channel. And here as well, from the inline direction. And then finally you get something like this, the 3D bodies, the 3D channels visualized in 3D. Okay, this is further reading, and that concludes this part of the presentation. We'll now continue with a quick demo. Thank you very much. Okay, the Thalweg Tracker is started from here, from this icon, And here we see the input, which is the seismic volume in this case. And we're going to pick a single seed position. Put it over there. And now we're going to track a number of voxels. And I'll put the number to 50,000. Tracking it. And we see a nice channel appearing. Now the colors in this case indicate the tracking history. And if I zoom in, you can see we have tracked individual voxels, and every voxel is colored by its history, so when it was added to the growing body. I can look at different attributes, for instance the Z value, the amplitude, and so on. Now let's go back at iteration, and I now can also save it either as a point set, as a horizon, as a volume, a cube, or as a body. And if I do that, it looks like this. So let me switch off the points, and you can see the body. And if I save it as a horizon, it looks like this. Again, switch off the points and the body. And with the horizon now also comes all the attributes. They have also been saved as horizon data, such as the iterations or the history, the amplitudes, and various others. Now the last thing I want to show is that if I start from a different position, let me switch off this, and I will now start the channel from this position over here. So I re-click, create a new seed position, and retrack from that position. You will see that I get the same body back. There you are. Now only the colors have changed because the history of the tracking is different. And that concludes this demo. Thank you very much for watching.